So we will get back to marine pollution a little bit later on. Now let's go back to the oceanography of the coastal oceans. Coastal waters obviously are relatively shallow. The shelf tends to be typically less than 200 meters deep. As you come closer to the coast, obviously, as we saw in beaches, the topography begins to shallow all the way to the beach or the coastline. They adjoin continents or islands. They're obviously heavily influenced by river runoff in terms of the sediment loads. You can hear some birds on my balcony. Sediment loads, wind forcing, upwelling, turbidity, tides, and human influence as well, right? And the open ocean lies beyond the coastal waters. Salinity can be highly variable, either because it's a dry evaporative region or a cold dry region like the California coast, or a warm rainy region like the Indian monsoon influence on the coasts, and so on. So the salinity can be very variable. All life has evolved. It's very humid and the throat keeps getting dry. All the life in the coastal regions have evolved for various levels of salinity. So when we go to biology, we will see the types of species that like very saline water and those that like very fresh water or brackish water, and so on and so forth. So the physics of it is such that if you have a lot of fresh water, you're going to cap the salinity layer below, so you can produce a well-defined halocline. You remember the salinity gradient, sharp salinity gradient. Mixing happens because of winds, because of tides, but also if it is dry. If you evaporate and increase salinity, you can increase density and you can have mixing. It's called convective mixing in the ocean. That can also happen. So broadly speaking, you have these kind of features. If you have high runoff, you get the horizontal scale abscissa here is the salinity going from low to high. So you can have a sharp halocline with low salinity at the surface and higher salinity at the bottom. Remember, it's still fairly shallow waters, okay? But you can have very high inflow like the Ganga Brahmaputra, for example, or the Columbia River estuary off the west coast of the US. And there are many such coastal regions. Dry offshore wind off of let's say Texas coast or African coasts, you can have high evaporation, which means the surface salinity will be very high, but the salinity below will be actually lower than the surface salinity. So you get a halocline, which is exactly the opposite of where you have high freshwater flow. Okay, so runoff and wind can mix and create a well mixed coastal ocean, which also happens in lots of places. Okay, so typical dry Mediterranean kind of climate can produce these. Temperature variability depends on where you are. In low latitudes, you have very warm layer which will create a thermocline and prevent the mixing, so you have restricted circulation. You can get kind of jets because the wind forcing, the momentum can get trapped in this very shallow warm layer. Mixing is prevented, so you can have very fast currents because of this strong thermocline. In the high latitude, you can have sea ice formation, which means what? Go back to your concepts. Sea ice rejects brine, which makes the water heavy, so you can have mixing and it can create isothermal. So you can have isothermal at low latitudes and high latitudes for very different reasons. Okay, obviously seasonality can be very strong when you go into the mid latitudes. Tropics don't have a very strong seasonality, except you may have a very strong rainy season and a dry season, right? So prevailing winds change, so even in the tropics winds can change. So even if the regional ocean may not have a strong seasonality and the land may not have strong seasonality, coastal ocean can end up having a strong seasonality because the winds can change direction like the monsoon winds. Okay, So this is just a schematic explaining that in the low latitudes you can have isothermal high temperature because the winds are mixing up in the eastern tropical Pacific. So if you again go back to your circulation, you will remember that where this is pointing is right under the ITCZ or the ITCZ, intertropical convergence zone, which is the rainy region, which is warm waters, rising air, expansion, cooling, clouds, etc. So the ocean is warm and well mixed because there are also so-called gap winds that are blowing from the Atlantic side into the Pacific side through these mountains in this Central American coasts. Okay. At high latitudes, as we said, sea ice formation can mix up, but you have low temperatures, whereas here you have warm temperatures. And in the temperate latitudes, typically you have summertime thermocline with warm surface waters and wintertime thermocline with cold surface waters. So you can get temperature inversion. So you have low temperatures near the surface and high temperatures in the deeper ocean of the coastal oceans. Okay. Temperature inversions also happen in the Bay of Bengal because of all the fresh water that caps the surface, forms a strong halocline and prevents mixing. And that can have many interesting effects. For example, when a cyclone passes by, you might get warmer waters mixing up as opposed to a hurricane which is bringing up colder waters. So there are some examples when a cyclone passes by over the Bay of Bengal, and behind it, instead of the water cooling, you can actually get a small warming or no cooling. So temperature inversions can have many interesting effects as well. Right.